we're gonna resolve rod cutting problem, and also we resolve 0 to 1 knapsack problem. So what is dynamic programming? As mentioned just now, in the event of having repetitive computation that needs to be done, then the dynamic programming, or in short we can call it as DP, solve the computation just once and save the answer in a table. Thus DP can increase efficiency. So just like the greedy algorithm, DP can be applied to optimization problem. So remember last week we learned about how we integrate dynamic programming with the Bellman-Ford, okay, to do the optimization to find the shortest path. So where we wish to find a solution for minimization problem or maximization problem. So any of these problem can be solved using any of these approaches. First is the recursive without the dynamic programming strategy. Okay, and secondly, we're gonna learn about dynamic programming top down, or we call this memorization. And third is dynamic programming bottom up, and we also call it tabular. Why we are learning these three different strategies is because from when we try to resolve the rod cutting problem using recursive without dynamic and memorization, then we can see that dynamic programming able to resolve a lot of, to reduce a lot of line code execution. Okay, so from there we can try to prove that dynamic programming is much better. So in this lecture, I just want to convince all of you. So later, you let's say you find yourself in industry having to having your assignment, you just don't start with doing the traditional recursion or iteration programming. Okay, please consider dynamic programming too, okay, into your design. So as mentioned, we would like to resolve rod cutting problem using dynamic programming. So this is a rod. Okay, so a rod can be anything. Okay, this can also consider a rod. It can be metal, it can be wood, from wooden, okay, anything that is long. Okay, so today we're gonna help this businessman. Okay, so you pretend yourself, this is you are a businessman that selling rod. You want to cut this rod to maximize the total value of the rod. So considering we have this rod, okay, let's say this rod is 4 inches. So let's say you decide not to cut this rod, right? You can sell this price at the price of 9 ringgit. Okay, then you want to consider, okay, should I cut to how many inches that I will make the most profit? Okay, so before we proceed, so this is the definition of the problem. Okay, we want to maximize. So this is a maximization problem. We want to maximize our value. So this is a rod. and N is the total length of the rod before cutting. So N can be any number. Okay, so let's say this rod is 4 inches, so my N is 4. So the following are the price of PI for different length of rod. So let's say this rod is cut into 1 inch. Then you can sell it for 1 ringgit. So let's say I cut this to 4 pieces, then I can sell these 4 pieces for 4 ringgit. Okay. So given a rod of length of N, example, during cutting your rod, your length of your rod is 4 inches. Find the most profitable way of cutting the rod. So now we don't see the algorithm yet. Okay. In your opinion, what is the most profitable way of cutting the rod?
Cut into 2 inches.
Cut it to 2 inches and you will get how many, how much?
10 ringgit.
You get 10 ringgit. Okay. Any other answer? So everyone agree? Okay, still, yes, yeah? Okay.
Yes.
So this is how our brain work. Okay, we can see it right away. Cut it to 2 inches and we get it for 10 ringgit. To ask things question, can I ask for assignment problem 4? Can we use the library for the DTW? Yes. Okay. So for the DTW, you can use the library. Any type of implementation is okay with me as long as you are able to implement something and explain to me the concept of the DTW. Okay, easy mark, easy 5 marks. Thank you for the question. Okay. So given a rod of 4 inches, so N is 4. Okay. We can cut up the rod of length N in 2 power of N minus 1 different ways. Okay. So let's say because for dynamic programming, what we do is we try to find all possible solution, then we pick the best. So our global solution is always an optimal solution. For sure, is optimal. Okay, because we already try all sort of ways. So in this way, we will try to so we can have 8 different ways. Okay, so how the computer works? In order to demonstrate this, I borrow my son's Duplo. Okay, so let's say we have 4 inch, right? So how the computer figure out is we make the first cut first. So this is the first cut. Okay, so we have 1 inch and 3 inch, which equivalents to B. Okay, then we can have something. What else can we do when we have the first cut? So today's class we're gonna play Duplo. What else we can do is we can have the first cut is 1 because we need to say what is our first cut. So first cut is 1. then we have this as one option. And we also have another scenario is using, sorry, this one is not dynamic programming yet. This one without the dynamic programming. So without the dynamic programming, we will have 1 inch, 1 inch, and 2 inches, which is equivalent to E. Okay, and what else? We can cut, this is our first cut, and then this one is the recursive function. And so we can have 2 inches and 1 inch. Alright, or when our first cut is here, we can have 1 inch, 1 inch, 1 inch, and 1 inch. Okay, so each of these will have a different value. For example, 1 inch, 1 inch, 1 inch, and 1 inch. For 1 inch, how much can we sell this?
RM1.
1 ringgit. So we can sell this for 4 ringgits. So that's how we get the age. Okay, then next is we consider that our first cut is 2. So when the first cut is 2, we have we can do 2 and 2. Okay, naively just now we get this is the optimal solution where we can earn 5 ringgit, 5 ringgit equivalent to 10 ringgits. And we also have another option which is to cut this. So we have 5 ringgit, 1 ringgit, 1 ringgit, 7 ringgit. What else? The first cut is 2, that's all we can do. Then the first cut is 3. So the first cut is 3, this is our only option, and our first cut is 4. Let me test you. So for this will be D. How much can we sell this?
9.
9, yeah? Alright, so you got the concept. Okay. So we can have this scenario for n power 2 power of n minus 1 different way if we use non-dynamic programming. Okay, so whatever that I just mentioned is using this recursive, it will take exponential. The time complexity is yes, it's exponential because it is like almost the worst case that could happen. Okay, because it needs to try all different scenarios. Okay, so later using the dynamic programming, we are able to resolve in such a way we do not need to do to have this to consider all these scenarios. Okay. So we see that cutting a 4-inch rod into 2 inches pieces produces revenue of P2 plus P2, which is 5 plus 5 is 10, which is the optimal solution. Okay.
Sorry, doctor, to interrupt, but I have a question.
Yeah.
For the formula 2 to the power of n minus 1, 2 tu dapat dari mana?
Okay, this two is just a generalization that we just want to say that, okay, the bigger the n, right, then the different scenarios that we have. This two, right, is the generalization. Remember when we were doing our lecture week 1 and lecture week 2, we try to have our generalization. This is it. It is from the book, but we can prove it. So for example, here is 2, n is 4, right? So 4 minus 1 is 3, so 2 power of 3. So 2 power of 3 is 8 times. So it can have 1, 2, 3, 4, 5, 6, 7, 8. 8 scenarios that we need to run in order to find all the optimal solution. So this is the generalization. So let's say we have n equivalents to 100. So it will be 2 power of 99, right? So you see how much scenario this algorithm going to run. So that is why the time complexity is very high. Did I answer your question?
Yes, thank you.
Okay, so I try to do some illustration to prove that it is 2 power of n. Okay. So this is the algorithm that we talk about. You see, it looks very short, but the time complexity is tremendously high. Why is it? Because let's say let's take a look at here. We have line 4, we have a for loop 1 to n. So in this case, we can have let's say n equivalents to 4. Okay. So at first we enter here, we do line 1, line 2, line 3, and then line 4 we already have a for loop 1 to n. Okay. So for each first for I equivalents to 1, right? Then we are going to have to do this line whereby it will call this function again. Okay, it will call this function again. When it calls this function again, it will enter. It will do this 1, 2, 3, and imagine it needs to run for I from 1 to n. Even in this call, right, we also need to do another for loop, whereby the first for loop we haven't finished it. We still I equivalents to 1. I over here is not equivalent to 2 yet. When we re-enter, okay, when we re-enter this n minus I, so it will be 3. So at first, cut rod 4, we are still at I equivalents to 1. Okay, then it will already call cut rod 3. So this cut rod 3 enters and will go do this, and then enter a for loop again, and then call cut rod 2. So this cut rod 2 will go inside again and will do this, and it's still for I equivalents to 1. Okay, so can you imagine like how deep this recursion can be? So that is why it is the time complexity is 2 power of n. Okay, wait. All right. So in this lecture, we just want to see how we live without dynamic programming. Okay. So the concept is cut the first length and recursively figure out the price you can sell for the remaining rod. Okay. Like so here, like I mentioned just now, so we have this rod. we cut the first length. So the first length can be 1. Okay. And then after that, this one is done recursively. This one will be cut rod 3. And then go into, and then it will cut another, it will do another cutting. Okay. Recursively. In order to get how much is this. So once they cut, and then they will return, then we will know that what happened, how much we can earn if we cut 1, 1, 1, 1. And then recursive if we cut like this. Okay. So don't worry, you do not need to memorize this. It's not really important. Okay, I just trying my best to do the proving to you because I want to do some marketing so that all of you will accept dynamic programming. Okay. So since we need to try all possible solutions, that is why we have a for loop before recursive function. For every value of I up to n, figure out how much we could make by selling a rod that length and recursively cutting out whatever is left. Okay. Alright. So cutting rod is inefficient. Okay, because it calls itself recursively over and over again with the same parameter value. It resolves the same subproblem repeatedly. Okay, so let us see why, which part that we solve it multiple times. Okay. Okay. Don't worry about this. I will explain about this later. Okay, but this is our n. Okay, remember our n first, our n is 4. Then let's say I equivalents to 1, n minus 1 equivalents to 3. Okay, because this one we cut from 4 inch and I equivalents to 1. I equivalents to 1, so the new n is 3. Okay, so this is how we get 3. Okay, so this 3, now we have cut rod 3. This cut rod 3, I is still 1. So remember our algorithm that is over here before we call another recursive function. This is P. P is like the array function that store all of the prices. Okay, so I won't talk about this. I just talk about this n minus I. So currently I is still 1. So now n is equivalent to 3 minus 1. So we cut this. Therefore, that is how we get our n is equivalent to 2. So we have we call recursively, we call cut rod 2. This cut rod 2, the first iteration, the I is still 1. Okay, so 2 minus 1 is 1. So we have this is how our n is 1. Then we call this our n is 1, n minus 1 equivalent to 0. So when 0, looking at our algorithm, when n equivalent to 0, then it will return. So when it return, it will return, and lastly we will get 4 ringgit for the first scenario that, so we can sell all this for 4 ringgit. Okay, and then we have like another scenario. Scenario first we have this 4, and then after that I is still 1. Okay, I is still 1. So we have this 3. So from this 3, right, like different other loop, right? So we have our I equivalents to 2, so we cut 2. So when we cut 2, then that is why our n become 1. Okay, then and then for this one, of course, we can it's like another recursive that 1 minus 1 equivalents to 0. I will tell you why cannot 1 minus 2. Okay, because it's the recursive function that they use that won't happen, that 1 minus 2. Okay, so whatever it is, right, just remember that this is the end. This is the rod that you want to cut. Right now, when we figure out this, we don't really literally cut the rod. Okay, the rod is not cut yet. We are just checking. What if we cut like this? What if we cut like this? The rod is still like this. So once we figure out what is the optimum solution, right, then only we literally cut the rod. Okay, we are just testing it in every scenario. So I want to I was trying to because this is from the book. Okay, it said that even in this small example, we resolve the length of n equivalents to 1 for 4 times. Okay, you see this one, right? We resolve it 1, 2, 3, 4 times. The same thing. That is why we did dynamic programming. We just resolve one and put it in the table, so that if later we have encountered the similar case, right, then we can just retrieve it to save time. And the worst thing is we resolve the zero leaf for 8 times. Okay, 1, 2, 3, 4, 5, 6, 7, 8 for 8 times. This one is when minus 1 means our n is 1 and I is 1. So 1 minus 1 is 0. Okay, and there are also some cases whereby our n is 2 and our I is 2. Maknanya we cut into 2. So this one we resolve for 8 times. Okay, it took me a few hours to figure out this. It's not really important for you to figure out, but I appreciate you if you can spend time to figure out how this recursive work, because when during the Viva session, right, I noticed that some of you didn't really understand about recursion, how it works. Okay, so using this example, I hope it can be the basis for you to identify. So whatever it is, I just telling you that, okay, let's say this is cut rod, okay, and our example is 4, our n is 4. Okay, so at first cut rod n equivalents to 4, the I can go from I1, I2, I3, I4, because for this for this iteration will loop until n. Okay, so when this one when it enters this the fifth line, right, is n minus 1, so it will be 4 minus 1, it will be 3. So now our cut rod is 3. So for cut rod 3, right, I until n only, so I 1, 2, 3. There's no I equivalence to 4. That's why we won't be getting negative function, negative value. Okay, so for the cut rod 2, okay, inside here 3 minus 1 become 2, and then it calls again, so it will be I equivalence to 1, I equivalence to 2 only. Okay, and 2 minus 1, 1. When we call cut rod 1, right, I can be only 1. Okay, because it's just 2n. Okay, but why this is execute for 4 times, right? Then because every time we run this, right, we need to do 1, 2, 3, 4. It's like inner loop and another inner loop. Okay, so whatever it is, although here we can only see 10 times of I, right? But the iteration happened for 16 times. Okay, 16 times. Okay, because even this one was done for 4 times. Okay. So in this slide, I just want to tell you how it works. So for example, we have the H. Okay, we cut 1, 1, 1, 1. So how this algorithm calculate, right? So for example, for this one, right, I don't use any sequencing. Okay, I don't detail out the sequence, which one it will do first. Okay, it's not really important, but I just tell you like whatever sequence there is, right? This was what happened for us to get 4 ringgit for this. Okay, so how this work is, first we call the card rod. Okay, this is the price and this is the N. So our N is 4. Okay, so our N is 4. So N is not 0, so we can proceed with line number 3. Line number 3 is Q. Okay, Q is the maximum price. Okay, for that particular N. Okay, so here 4, then we will call this, I just copy this here. So N is 4, I is 1. So 4 minus 1 is 3. Okay, so we will call card rod 3. This card rod 3, our N is 3 and our I is still 1. So 3 minus 1 is 2. So right now minus 1 means we cut 1 inch. I is like how much we cut? We cut 1 inch. From here to here. Then from here to here we cut another inch. Then from here to here we cut another inch. So right now our N is become 1 inch. So 1 inch, basically we don't really need to cut, right? So it will become so once is 0, right? Then it will return 0. Okay, so when it returns 0, right, you can see here is PI plus card rod. So this card rod is was written 0. Okay, so we can put it here as 0. And this is plus, and this PI is the basic data structure. PI means the price of I. So currently I is equivalent to 1. So PI is 1 ringgit. So 1 ringgit plus 0 ringgit means this card rod 1 will return 1 to the caller. Okay. So now the caller is 1 ringgit. PI. What's the value of I here? I is still 1. Okay. 1 ringgit. So 1 ringgit plus 1 ringgit is 2 ringgit. Then you will return 2 over to the caller. Okay, 2 ringgit. So same. PI is still I equivalent to 1. 1 plus 2 is 3 ringgit. So it will return 3 ringgit to here. And so lastly, it will return 4 ringgit. So it's true, right? Just now, if we cut this into 1, 1, 1, 1, then we will get 4 ringgit. Therefore, we will we will get this answer for one scenario. So we have 8 scenarios. So basically, we just do the same thing. Okay. So the next one, we just repeat it. Okay, as I said, this slide is not very important. You do not need to memorize. I just want to show you the hassle of doing this. Okay, so right now, let's say we want to cut 1 inch. We want to cut 1 inch. 1 inch, 1 inch, and 2 inches. Okay, so what we do is at first we have 4. Okay, 4, and then we cut 1 inch, and then after that we cut another 1 inch, and then after that I equivalents to 2. So we have this 2 inches. Okay, so we want to know how much. Okay, so any equivalence to 0 will return 0. And then this, how much will this return? This will return 5 ringgit. Okay, so how much this and this will return? It will return 6 ringgit. And then how much all this will return? It will return 7 ringgit. Okay. Then we have the third scenario. So you see here, this is how this tree looks like. Now we here we return 4 ringgit. Here we return 7 ringgit. Here we return 7 ringgit if we do the same way. Okay. We just okay. So right now in this scenario, we want to firstly our first cut is 1. Okay. And after that, we cut to 2 cm, and then we have 1 inch, and then after that we return. Okay, so 1 inch because we need to resolve the deepest recursive, right? So this one will return 1 ringgit. This one and this one will return how much?
6.
6. Okay, good. Okay, so this one, and this one will return 1 ringgit, 5 ringgit, 1 ringgit.
7.
Okay, good. Okay, let's try again. Let's take a look at our fourth scenario. Okay, so in our fourth scenario, our first cut is 1. Okay, so this is our first cut. So for our first cut, and then after that our second cut is 3, so we do not need to do anything about this. Okay, it becomes 0. So this will return how much? 3 inches will return how much? P3.
8.
Okay, 8. So it will return 8. So 8 and 1. Sorry, 3 inches and 1 inch will return how much is this?
Return 9.
Okay, so this one is 1 ringgit, this one worth 8 ringgit, because this one is 3 inches worth 8 ringgit, so it will return 9. Okay, all right. So same as this, but this time our first cut is 2. Okay, so for the 2, right, it will just return 8. Oh, sorry, it will start with this one first. Okay, so it will return 1, and then after that when we consider this, it will be 2 ringgit, And then 2 ringgit plus 5 ringgit, then it will return 7. Okay, who does not understand so far? So we already have first scenario, second, third, fourth, and fifth. Okay, and the sixth one is where this is the optimal solution. Okay, so the first cut is 2 and the second cut is also 2. So this will return 5 ringgit, and these two will return 10 ringgit. So the revenue will be 10 if we cut this way. So by far this is the highest. Okay, and the last two scenario is our first cut is 3. So our second cut, no choice, only one way. So this one will return 1 ringgit. 3 is 8. So 1 plus 8 equivalents to 9. So if you cut this, then you can get 9 ringgit. And last is we don't cut at all. Okay. So when we don't cut at all, our PI is 9 ringgit. Okay. So we don't cut at all. So in this example, right, it tells us as if there is no cost of cutting. So you might find other problems that have the cost of cutting. So you can minus that, how much you sell minus the expenses. Okay, but in that maybe they already put in the price for the revenue. So okay, we don't consider that. So this is how we know that we have tried all possible cuts, so we can make decision where to have our first cut. So our first cut is 2 and our second cut is 2. Okay, so this is how computer thinks without dynamic programming. Okay, so in terms of time complexity for n equivalents to 4, of course, if this is asymptotic analysis as I have described earlier, if asymptotic analysis we cannot do when n is small. Okay, but we just try, because if I want to do n equivalents to 100, it will be the example will be too long. So we can say that we call our recursive function for 16 times in order to figure out 8 different ways. Okay, which is n power of 2 minus power of n minus 1. So this is exponential time. So why is cutting rod is insufficient? Okay, the problem is that this algorithm call itself recursively over and over again with the same parameter value. They are resolving the same subproblem repeatedly. Okay, so that is when we now try to resolve the rod cutting problem using dynamic programming top-down memorization. Okay. So for the memorization is the concepts are all the same like we discussed just now, but there are two differences. Okay, only two differences. First is they memorize they memorize the previous solution. So if that solution has been resolved before, then they just call back. Okay, that is the first advantage. Second, why it is more efficient is because using this dynamic programming, they don't look at all of the scenarios. Okay, for example, just now we have, what if the first card is here, and then after that we do this and this. But how about we don't cut it, we do like this. So there's like eight different scenario. But for dynamic programming, they don't consider, we do the table, but we just assume that what if we only have 1 inch, okay, what is the best? So it's not that we do not need all other scenarios. That's why it is more efficient. Okay, like what if we only have 1 inch? What would you do about it? What is the maximum revenue that you can get with 1 inch? That's all. Then we save inside the table. And then we say, okay, what if we have 2? We do not need to talk about what if we break this. Okay, no, we do not need to do that. What if we have 2 inch? What is the maximum profit that we can get? That's all. So later, when you have like a rod of 8 inch, whatever, then you can just refer to the table. Which one is the, something to do like the ratio, okay, which one is the best for you to take, okay, for you to cut. So let's say the highest value is 2. Okay, you look at the table, the highest value is 2, then just cut all to 2. Then let's say it is odd number, it's like 9 inch, so you have 1 inch left, then you just refer to the table. Okay, for one, what is the best? 1 ringgit. So there's no need scenarios. So that is why it is more efficient. 1, it memorized. 2, it doesn't go through all scenarios. Okay, so over here, how they do it is by adding. Okay, this line 3 to 7 is exactly like the naive recursion. Okay, but what they added here is they check if the desired answer already known, then we just return it. No need to do 3 to 7. And of course, when we have compute this, right, we save the answer. That's the difference. Okay, in terms of the algorithm. Okay, so let me just introduce you this. Okay, so the concept is the same as the naive recursive. Okay, we cut the first line. Right now, this is Rn, is a new array for memorizing of the maximum price to sell. Okay, then this one are all the same line as the naive. Okay, okay. In order to understand how it works, we straight away go to the example. Okay, we take the exact same example as knife, whereby we have 4 inches of rod. Okay, and then the price is exactly the same as our previous example. So right now is this whole thing. I just copy from here. Okay, R1 max. What is the maximum value for the price? And then and this one is when n equivalents to 1. We just want to know, let's say we have this one, right? How much money we we can earn. Okay, maximum. Okay, so what you need to do is price 1. Okay, price 1 is 1. Okay, so let's say is this one is n minus 1. N minus 1. Our n is 1 and our I is also 1. Okay, so this is 0. So if it is 0, right, then we need to return 0. Okay, it needs to return 0. I didn't copy the algorithm there. Okay, so we know that, then we save this the value of the maximum value that we can get to 1 ringgit. We just save it. That's all. We're just gonna do one time. Okay. Then, if you're not clear, I hope as I keep on repeating for the next example, then you can understand. Next is we have a rod of 2 inches. So we want to know how much is the highest value we can get to sell this. So we can see that over here the first iteration is price 1, and then okay, hold on. Okay, so is 2 minus 1. Our n is 2. Okay, and our I is 1. Okay, for us that is 1. So 2 minus 1, we will call back this memoirs cut rod auxiliary. Okay, so we check right now is, do we have because this one is R1, so do we have R1, is it bigger than 0 or not? If it's bigger than 0, means previously we already saved the value. Okay, so right now R1, okay, this is R, and this is when n equivalents to 1. Okay, yes, we already saved. Okay, we already saved. What did we save? We save 1 ringgit into our memory. Therefore, we call back the 1 ringgit. Okay, so we get this value of n equivalents to 1, okay, which is 1 ringgit. So the price of 1 is 1 ringgit. 1 plus 1 is 2. Okay, so this is when we know that this is the one if we cut it into 2. Okay, I did mention that we don't go through all scenario, but we don't go through all 8 scenarios, but we using this algorithm we still need to go through some of the major scenario, okay, but not all. Okay, next is, if you follow this, then we will need to do, hold on, sorry. Then we have like another scenario where we don't cut at all. Okay, so the price of 2 is 5 ringgit, and then 2 minus 2 is 0. If 0, it will return 0. So 5 plus 0 is 5 ringgit. So now this is the use of the maximum. Okay, so we have 2 ringgit or 5 ringgit. Therefore, we just only store the maximum value, which is 5. Okay, so we put here as 5 ringgit. This is already inside our memory. So the optimal cut is to have no cut at all and just leave the rod of size 2. So we don't cut at all. Okay. Then we move to 3. We move to 3. Okay, so for 3, we can have some scenario 3 minus 1. Okay, so the first price is the first cut is 1, and then the second cut is 3 minus 1, which is 2. Okay, so what we do here right now, we do have the memory of Memoirs cut rod auxiliary 2. Okay, because we check R2, is it bigger than 0? If yes, then we should return the R2. What is R2 now? R2 is 5. Therefore, we return 5. Okay, then we will get 6. 6 ringgit if we cut it this way. Okay, so then you will do the same for the second one, which is price 2. Okay, and then we need to retrieve the Memoirs cut rod of 3 minus 2, which is 1. Okay, so 1 we already have, right? 1. So here we can retrieve R1. So R1 is here. Okay. So therefore R1 we can put it here without needing to recalculate. This one we do not need to recalculate. It's just like price 1. This one is price I. So let's say I equivalents to 2. So price 2 is 5. So that's why 5 is here. Okay. So right now, price number 3. Price number 3 is P3 is 8. So that's why 8 is here. Okay, plus 0, because 3 minus 3 is 0. So it will return 0. Okay, 0 ringgit. If you don't have any inch, then you can just return 0. Okay. And lastly, if we have cut of 4, okay, with a cut of 4, so first is first is this scenario, okay, where we have the first cut is 1 cm. So price 1 is 1 ringgit. P1 is 1 ringgit. RM. And then Memoirs cut rod 4 minus 1. Okay, we already have the answer. So we do the checking. 4 minus 1 is 3. Okay, so right now R3. R3, we look at the table. Okay, great. R3 is inside here. Okay, so therefore we do not need to recalculate. We just update it into here. So we will get 9 ringgit. Okay, so the rest speak itself. Okay. So 4 plus 2. This 4 minus 2. So which one should we retrieve from? So this price 2 we get from here, and this will get from R and 2. Okay. And price 3. This price 3 we get from here. Memoirs Cartwright auxiliary 4 minus 3 is 1. R1. So we will get from here. Okay. That's why 8 plus 1. Lastly is price 4. Price 4 we will get from here. Okay. And Memoirs Cartwright 4 minus 4. 4 minus 4 is 0. Okay. So that's why we get 10. So right now we have a full table of this. Okay. How much we can sell? So the best in here, how we gonna look at it? Let's say we have 4 inches, right? The best is 10. 10 is when our first cut is 2 and our second cut is 4 minus 2 is also 2. Okay, so this is how the dynamic programming works, and the time complexity to perform this is n square. Okay. So we're gonna do the same thing now using tabular. Okay, because remember just now we have 3 approaches. Okay, naive without dynamic programming, memorization, and tabular. So we're gonna learn about the tabular. Okay. So for tabular, it remember the previous result computed, fill the table left to right without recursive call. So right now, we are doing iteration. Okay, so for tabular and for memorization, it gives the same, because it is just how they implement it. Okay, so it does give the same time complexity, but I just want to tell you, even though they do have the same time complexity, a recursive algorithm always have some overhead because it needs to call like the entire function, so it does give some overhead on managing that. That is why the best is to use tabular compared to the memorization using recursive. Okay, so let's just go through our last approach, okay, which is dynamic programming bottom-up tabular. Okay, so now we start from j equivalents to 1, and it needs to traverse from I to j. Okay, so they give another variable j here. Okay, then we will need to do this q. Q is the maximum revenue for that particular n. Okay, which is maximum price I. So currently I is 1. Okay, plus r j minus I. Okay, so right now I just feed in this information inside this equation. So we have price of 1 plus r 1 minus 1, because j is 1, I is also 1. Okay, so the value here is 1. So we just update when we have 1 inch. Okay, and the price of 1 inch is 1 ringgit, and the optimal solution will the optimal revenue that we can get for this n equivalents to 1 here is 1 ringgit. Okay, so we just go through, repeat the same process, whereby right now we increase because previously there's only one max value. Okay, why? Because for this, right, I to j, so I is already reaching 1, so we finish it, we break out from this loop, and then we re-enter again where j equivalents to 2. So when j equivalents to 2, so we have two maximum values. Okay, so let us just try to do this together. So our j is 2 and our first I can be 1. Okay, when I equivalents to 1, it will be price 1 plus r j minus I. So 2 minus 1, which is 1, equivalents to 1 plus 1 equivalents to 2. Okay, next is I equivalents to 2. Okay, so the price is 2 plus r j minus I. So j is 2, I is also 2. So that is why is 5 plus 0, which is 5 ringgit. So from here we have two options, 2 and 5, because we need to make the maximum, right? Take the maximum, therefore we take 5 and update into the table. So right now, just like how we understand naively, let's say we have 2 inches and the best revenue is is 5 ringgit. Okay, where we don't cut it at all. Okay, so right now I cannot go to 3 because j is only 2, therefore we break this loop and go back to line 3. Now j become 3. Okay, so when j equivalents to 3, we have 3 different scenarios that we can take a look at, which is I equivalents to 1, I2 and I3. So again, we feed in all the information inside here, because this one is the price of I. Okay, PI. So PI, this is 1, PI2, PI3 plus, and this is J. So now our J is 3. So 3, 3, 3. Okay, so J minus I. So right now I equivalents to 1. So 3 minus 1, 3 minus 2, and 3 minus 3. Okay, so from here we can get 6, 6, and 8. Okay, so we know that the maximum price that we can get is 8 ringgit. Okay, 6688 is the maximum. So we update when to 8 ringgit. So we see here that if we have a rod of 3 inches, the maximum value that we can get is 8, whereby we don't cut it at all, right? So right now it will break the I4 loop and re-enter line number 3 when next J is equivalent to 4. Okay, so when J equivalent to 4, I has 4 different, I can go from 1 to 4. So again, price 1, price 2 inch, price 3 inches, price 4 inches. And then the R will be J minus 1, J minus 2, J minus 3, and J minus 4. Okay, again, then we will get the revenue for each scenario. And we pick the best, the maximum, which is 10, and we update into the table. So right now we know that if our J is 4, when we have 4 inches, the best price is the first cut is 2 and the second cut is 2, where we will get 10 ringgit. Okay, so right now based on this table, we can say that, okay, if we have a rod of 3, the maximum revenue that we can get is 8. Okay, if we have 2, the maximum revenue, then we have 5. Okay, so let's say we have like a rod of 8, right? So we can use this to manipulate. It depends on the problem. Maybe the problem said that length of 5, then they have some other tables. But if this is it, right, then you can we can manipulate this table in order to get the best revenue. Okay. So right now, this can be used for business. Okay, so let's say you have some even if somebody is selling rod, so their rod can be varies. The value of rod can be varies. Okay, and when you have this table, then you can reuse this for all sort of end. Okay, but still it depends on the problem. Okay, we need to tailor to the problem, because they might have like different cut that they want to cut. What if 10? Okay, but if the highest that they want to sell is 4 inches, then you can keep on reusing this. So for this algorithm, right, it's just give you the idea, okay, for you to apply anywhere that you need in the problem that you solve. Okay, so right now you can see here, right, using dynamic programming for this kind of problem that keep on having to resolve the same problem again and again, right? Then you can consider using dynamic programming, because to reduce the time complexity. Okay. So right now, I did explain about the memorization and the tabular. So these two approach yield algorithm with the same asymptotic running time. Okay. So this is from the book, saying that the bottom-up approach often have much better constant factor. Okay, since it has less overhead for the recursion call. Okay, so for the recursion call, it gives us some overhead. That is why bottom-up approach is better. Okay, so because of this, right, for our last problem, which is the next set problem, 0 to 1, right, take it or leave it, we will use the tabular dynamic programming. Okay, so in here I give a different way for you to apply. Okay, this is like the extent of how we want to apply for the rod cutting using tabular. You can also do it like this. So when we learn about the greedy algorithm, we did talk about this greedy thief who wants to take maximum value of item. So it's still maximization problem. So let's say we have the same exact item 1, 2, 3, and the value and the weight are also the same, and he's also using the same knapsack, which W equivalents to 50, exactly the same one as in our greedy lecture. Okay, so to revise, which item should he take? Okay, which item should he leave behind? So this is the knapsack algorithm. Okay, I should have written algorithm here because this one is a pseudocode. Remember, in your group project later, pseudocode must be readable. Okay, so let's try. Let's to simplify, right? Just to understand the concept. Let me just explain to you how we can utilize dynamic programming, okay, to resolve this one-to-one exact. So right now we have n equivalents to 3. N stands for the item. So we have item 1, item 2, and item 3. Okay, so n has 3. Okay, and the weight is 50. All right. So what you do is you build a table like this. Okay, the rows are the items, and then the columns are the weight. Okay, so for this weight, right, you can imagine that the thief put in the bag like bit by bit. Okay, so at first the bag is empty, and then what happened when he put something 10 kg of weight, and then 20, 30, 40, lastly the next set is full. So um, what we have here, the first row is when there's no item at all. Okay, when there's no item at all, then we can just put our value as 0 all the way. Okay, and let's say in this bag do not have anything. So if it does not have anything, 0 kg, so we can put the value as 0. So inside this table are the value. Okay, so the concept for dynamic programming is, for example, for the first row, we will just consider to take item number 1. Okay, so item number 2, item number 3, we don't take it at all. So this row only consider item number 1. When we reach here, right, at item number 2, means we can take item number 1 or number 2. Okay, can take both. And then when we do this final row, you can take item 1, item 2 and item 3. So the value here will keep on increasing. Okay, for this example. Okay, so let's say you have some other example where the weight does not really relatively increase with the value, then you can have different table. Okay, so right now I just want to tell you beforehand that this algorithm is not complete. Okay, because it doesn't really trace what are the item that needs to be picked. Okay, so you need to add your algorithm to trace what are the items. Okay, so let us proceed. So right now at 10 kg, let's say the bag has 10 already filled 10 kg, the value will be 60 ringgit. Okay, and this one is the notes. We do have the method. Okay, when you do your lab viva, you will need to try to I identify how to track this. Okay, otherwise the lab viva, sorry, not the lab viva, the lab will be too easy. You can just copy and paste the source code and try to run it. So you need to identify how this being tracked. Okay, but this one we just try to do naively. Okay, all right, so when it is 20 kgs, the value will still be 60 ringgit. 60 ringgit, 60 ringgit until 50 kg, because for 0 to 1 knapsack, the thief can only steal each item he can only steal 1 unit. Okay, so there's no choice. Okay, it will still be 60 ringgit. Okay, so since we are considering item 1, even the capacity reached to W, the value is still 60. Alright, so we still take the item number 1. Okay, let's take a look at when we are able to consider 2 items. Okay, so when we can consider 2 items at 10 kg of capacity, we cannot fit item 2. Okay, because item 2 is 20 kg. Here at this point is only 10 kg. So we will stick to value of 60. But when we use the capacity of 20 kgs, then the highest value is when we ask the thief to take item number 2, which is 100. Therefore, I put here item number 2, 100. Okay? Get the concept? Okay, let's try. Now, at capacity 30, what is the highest value? At 30 kg. $160. Okay, correct. Okay, Because at capacity of 30, we can take both item because both item 10 kg, 20 kg can be fit into here, and the value is 60 ringgit plus 100 ringgit, which is 160. So for 40 and 50 kg, we it will still be the same value because we can only take one unit of item 1 and one unit of item 2, and at this point we have yet to consider item number 3. Okay, so just put 160 over here. Okay, next is when we are able to consider all items. Okay. So the first 10 kg is still 60, the second 10 kg is 100. Why is the 30 kg is 120? Because when we use greedy approach and our weight is the consideration factor, so we need to be greedy about our weight. Okay, so that is why based on this weight, the highest we will take is 30 kg. That is why it is not item 1 and item 2. Okay, and okay, then let's try at capacity 40 kg. What would be the value? Yes, is that correct? Okay, any other answer? So it will be 180. Okay, good. Most of you get the answer correctly. Okay, because at capacity of 40 kg, we can get item 3 and item 1 into the bag. So it's 180 kg. Okay, so at capacity 50 kg, what will be the value? Alright. Okay, very good everyone. 220. Okay, so as I said, this method described does not tell which subset give the optimal solution. The annotation is just for us to understand the concept. So you need to find out the method while you are answering your lab questions, okay? Because they do have the comparison and okay, about this. So you need to study more on how you can do this tracking. All right. So let's do one practice question and then we finish for today. Okay, let's test our understanding. So right now we have n equals to 4, so we have 4 items, and then our weight, the maximum weight is 8. Okay, so now we are considering item number 1. Okay, so what will be the value here? Two, 0. Desmond said 1. Mona said 0. 0, 0. Okay. Okay, decimal also said 0. Okay. Okay, it will be 0 because at capacity of 1 kg, we couldn't even fit item number 1. Okay, so what about this? One. Okay, good, very good. Okay, where we can fit item 1. Okay, next is 3 kg, 4 kg, 5 kg. What would it be? One also, Cairo. One to all. Very good. Okay, one to all because we can only pick one unit for item number 1. Okay. Now we need to consider 2 items. For 2 items, for 1 kg of course is 0. We already answered that. 2 kg is also 1. Okay. Okay, how about at 3 capacity of 3 kgs? Two, three, three. Okay. Yes, 2. 2. And then Desmond said 3. Are you sure, Desmond? At capacity 4. Okay. Okay. Dizzy already. I understand. Okay. So 2, yeah. It's still 2 because at capacity 4, here is 3 kg, here is 2 kg, so we cannot add it. So we just take value of 2. How about 5 kg? 3. Others? All 3? Okay, good. So the rest are all 3, okay? Okay, 2 more row, then I'll let you go. Okay, now we are considering 3 items. So here should be the same. Okay, at capacity 4 kg. What would it be? Desmond said 5, Moni said 5, Farid 5, Haziq. Okay, good. Okay, 5. At capacity 5 kg. Kishore sure not 6. Yongming, yeah, okay. Okay, at capacity 5 kg, we have 4 kg, and then here we cannot put into, okay, item 1, because item 1 is 2 kg, so still 5. Okay, Kishore, correct. Or Shu Hui, correct. Okay, how about 6? 6 is 6. I already give the answer. So at 7, at capacity 7 is 7, 2 and 3. Okay. How about 8? Last one. Still 7, yeah? Okay. Last row. Good job, everyone. Last row. Alamak. Farid said 10. Loy Jin Hong said 9. Okay. Over here, is it? Okay, over here. At capacity 8 kg. Okay. Farid, we cannot put 10. I think because you want to put this 4 kg item 3 for 2 unit, but for the 0 to 1 exact problem, we can only put 1 unit, so it cannot be 10. So although this item 3 give the best, the highest value, we need to pick others. So right now we have 8, and then after we put item 3, we have 4 kgs left. So 4 kgs left, we can either take 2 or 3. Being greedy, we will take 3. So 3 will have the value of 2. Therefore, 5 plus 2 equivalents to 7. Okay, I think those that said 9, right? Maybe you got confused with the weight. Remember, in this table it has to be value because we are trying to find the maximum value to tell the thief. Okay, it's a little bit lack of moral to be helping the thief. Okay, but it's okay, we are all bored due to lockdown. Okay, we just help the thief. Okay, last row. Last row, when we are able to consider all 4 items. Okay, give you a shortcut. Okay, at capacity of 5, what will be the value? Six. Oh, okay, you answer 6. Okay. At capacity of 6, what will be the value? Six two. Moy, Haziq, Yomi, all correct. Kishop correct. Arik correct. Desmond also 6. Okay. 7. 7 is 7. Okay. Very good. And lastly, 8. 8, 8. Okay. Okay, good. Correct. Okay, so now you have learned the concept of dynamic programming, but you can try to do our lab. Okay, I don't mind, you can just copy paste from the source code, but please try to understand how they implement it. Okay, and it will be better if you include some of additional algorithm. Let's say you want to do the tracing and all. Okay, but most importantly, you understand what is the concept of dynamic programming. Yeah, okay, then you can start thinking on how to apply into the real life. So for instance, we learn about the Bellman okay, when the dynamic programming is applied in graph strategy. So for Velma, remember we check all of the edges for number of vertices minus one time. Okay, we will keep on checking. So for then we will get the global optimum. Okay, you have to remember we have the local optimum and the global optimum. For greedy, right, if we just use greedy without because greedy won't will not see all of the possible solution. It's just based on the optimal, and then it will just leads from there, which sometimes will not lead to global optimum. But using greedy, for sure you will recommend the best. Okay, whatever recommendation system that later you are going to develop, please consider dynamic programming because it consider all of the solution. Just like for the next set problem, we consider all of the solution. Okay, and one more thing, because usually every semester, right, we do have so now we stop at dynamic programming. Okay, and I feel that another way to make our software program faster is using the multi-threading. Okay, so multi-threading is what you're gonna do self-learning for next week, because multi-threading is something that, let's say we have algorithm, and we need to identify which line that can run concurrently. Okay, when it can run concurrently, then we will get faster faster program. Okay, so let's you see you merge dynamic programming and multi-threading, right? Because dynamic programming, it does give us a lower time complexity, because just now we already seen that using the naive recursive without dynamic programming, it will take exponential. Okay, but using dynamic programming, it will just take n square. Okay, so for multi-trading, just to introduce, and hopefully you are interested to apply this, is when we have algorithm, then we will assess, okay, which line or which function, doesn't matter, that can run concurrently. So we will declare, we will put some syntax saying that, okay, from this line to this line can run concurrently with other with other um, with other set of line or with other set of function. So your computer program will give faster input. Of course, there's some limitation, because it is also going to have constraint on your processor. But if I'm not mistaken, I have read once, like, correct me if I'm wrong, because I know you have taken one of the course about this parallel programming. Have you taken that? I'm not so sure if I've taken it, but from my reading, if we have the core duo, a single processor, for multi-threading, we can run up to three concurrent program. I'm not so, I can't really remember. I have to read back. Okay, so there's some, what I'm saying is there's some limitation based on the performance of your PC, but even for the core processor, multi-threading can be executed. So um, in conclusion, for this course, right, since this is going to be the last time we meet for the lecture, when you want to come up with the algorithm, you have to try to design in such a way it will give low time complexity. Of course, you need to solve the problem, okay? At the same time, low memory consumption. Okay, it's no longer like okay, I just write lah. I feel like writing like this, or right now is like we used to copy the source code and then edit it. There's nothing wrong with that, but you can improvise. And let's say when you are working, right? Because I used to work in industry too, and I was a programmer myself. We inherit the source code from our senior. You know, there's like no way we can tell our senior, hey, you know what, your programming, give very high time complexity, and okay, it's kind of difficult when you inherit the source code. But I want you to bear in mind, whatever, maybe you can fix it. Okay, try to fix it to make it better. But if you totally inherit it and edit it, no choice. But let's say you need to reprogram a new program, right? So you have to consider what you have learned in this algorithm, and hopefully, because one of the factor that people be feeling at ease using our software system is also the speed of it. Okay, if there's a lot of lag, um, then it is very dissatisfying. Okay. So it's important because even for algorithm, you can see that using recursive, right, it will take 16 times to do the processing. So our PC can be hanged because of the poor design of the algorithm. So at first, the name of the course is algorithm design and analysis. So you design first, then you analyze whether the time complexity can be improved or not. Okay, bear that in mind. I have a question here from Izzat. From column 6 kg, isn't 6 from 5 plus 1, which means item 3 plus item 1. Item 3 plus 4, column 6 kg. Okay, we are consider. Is it this one? Are you asking about item 3, item 1? I think, is that you're talking last row? Okay, last row. Last row here, is it? Last, okay. Last row at 5. Why is it 6? Okay, hold on, yeah. Why is it not 5 plus 1? Okay. I understand. So, for this row, because 0 to 1 knapsack, it's still it still use greedy, because the consideration factor, the factor that has limit here is weight. Okay, so because of that, right, we need to see which one is the heaviest. Okay, is that so? Right now, at 6, we have capacity of 6. Capacity of 6 right now. The heaviest that the thief want to put inside his bag should be the heaviest. The first that the thief want to put inside his bag, it should be the heaviest. That's why he take item number 4 instead of item number 3 and item number 1. It's because item number 3 is 4 kg. So it's not really brilliant, right? Because if we are the thief, right, Then we will take the highest value first. I don't know. Would you? Okay, but this is the rule. Understand, is that? I think he meant that the chosen item should be item 1 and 3 instead of item 4. Yes, yeah, I understand. But in this case cannot, because we have to take the heaviest item. Because right now at weight 6, we can take any of this item. Okay, because weight is the consideration factor, means we have to pick the highest weight, which is 5 kg. That's why we need to put 6 as our value, because at 6 kg then we can no longer put item 1. So the chosen item should be item 4. Remember, yeah, is the consideration factor. So the consideration factor is the item that you first need to put. Since the consideration factor is weight, then we need to find the heaviest one to put inside our bag. Sometimes, instead of weight, it can be space. So for the space, we have to pick the biggest space to put in our bag. It's just that when we want to pack our bag, right, we always have to put the biggest thing first. Let's say if we put small things, right, the biggest thing cannot be insert. I think that's the concept. From Moy, for this knapsack problem in dynamic programming, we are no longer considering the value weight and take the portion of weight to put into the bag. All items should be in discrete form. Okay, next set problem. I don't understand your question. It is the same concept, but it's just that between the rod cutting and the knapsack, I use different way to make it understand. I feel that there's like two way, but it's the same. You can put you can use the same table for the rod cutting to the knapsack problem. It's the same. It's just the representative of answer. I did it differently. I don't understand what you mean by item should be in discrete form. Value divided by weight should be the most valuable item, right? Okay, that one is for the fractional knapsack problem. So, if you want to do that, you can also apply dynamic programming. But in this case, we are doing the 0 to 1 knapsack. So we do not need to measure the ratio. Okay, Stanley, he means that we can take the bag partially. Okay, that one is fractional. Fractional knapsack. Remember, knapsack problem has two. Okay, one is 0 to 1, take it or leave it. And another one is fractional knapsack problem, the one that we can cut. it can also solve using dynamic programming. Because the fraction, right, give more value, right? Because we weigh the like Moy said, value divided by weight. Okay. So some of the common question asked about the group project, right? You say that do you need to come up with the GUI? You know, I'll be happy if you come up with the GUI. Okay, but in order to get full mark, you don't need to. But I'm very happy if you come up with the GUI. What are the common questions? Some keep on questioning themselves whether their solution is correct or not. Okay, just you need to trust yourself. Okay, and you just, because when you are working, right, you'll be given some problem and you need to solve it. So that's why this is designed as problem-based learning. You will learn when you want to solve the problem. So when you find some problem, right, you need to do some searching. Why is this? Why is it that? Right? That will help you to learn on how to design. We purposely do it as problem-based learning. Okay. So okay, is 1 minute to 5 p.m. So I wish all of you to stay safe, everyone. Okay, the situation here, I think is quite is worsen, right? So stay safe, everybody. Pray for me because my husband's colleague, the wife just got positive. So I hope there's nothing happen. Okay. My husband met his colleague last Thursday, so please pray for us, okay, that he's negative, otherwise we become the close contact. Okay, so goodbye all, stay safe, bye.